Hello, everyone, and welcome to the Sampling Methods, Mass Analyzers, and Detectors training. My name is Grace Albright, now Grace Topol, and I'll be taking you through the different types of sampling methods, mass analyzers, and detectors. All right, so to start off, we have three different types of forensic samples, according to Hussein, that you might encounter at some point in your career. To start off, we have physical samples. These are going to be the question documents, trace samples, and impressions. Next up, we have our chemical class. This is going to be drugs, explosives, and other assorted toxins. And lastly, we have the biological samples, which include things like semen, blood, and vomit. Now, when it comes to sampling preparation techniques, when preparing these different types of samples for things like chromatography and then further analysis by mass analyzers and the detectors, it's surprising, but the preparation is very similar with some variations, of course, depending on the type of evidence. To start off, for example, if you might be dealing with physical evidence, but really it's like a question document and you need to perform an extraction or would like to perform an analysis on the ink, you will need to use a type of extraction method in order to extract that, whether it be solid phase or liquid, just some way to get that ink separated from the actual document for further analysis. Now, most of the evidence, though, can be dissolved in an appropriate solvent in order to get it prepped and started. Usually like dissolves like, so if it's a polar component, polar solvent will do the trick. And the solvents are often organic as well. But this way, once your sample is dissolved, the mixture that is formed from it is either going to be left in the liquid form, either methanol or acetonitrile base, along with that mixed in evidence in there to be run through HPLC or LC chromatography, or it's going to be volatilized for analysis. And this can be confirmed by PITS documents. For our first mass analyzer and detector pair, we're doing quadrupole with continuous dynode electron multiplier detectors. So as you can see in the image here, a quadrupole is that for a reason, 4 poles. It's measuring the mass to charge ratio using these 4 poles as well. To do that, it takes basically an oscillating or alternating currents running through these poles. These currents can be adjusted in order to create magnetic fields, which will affect the ion trajectories, allowing for a more specific separation. According to Thomas, quadrupole can be so specific that you can narrow it down to just a singular ion if that's the only one that you're trying to receive. Any ions that don't necessarily match or work for the type of M to Z calibrations that they made for the magnetic fields are going to be basically just deflected away from the ion detector, and only those specific ones are going to reach the detector. But the detection will occur when the ions hit the dynodes. If there's sufficient kinetic energy in those ions, then the secondary electrons are going to be produced and continue on creating this electron cascade. Their collision with curved surfaces is what's going to cause the signal multiplication. As you can see in this bottom diagram there, it just gets bigger and bigger, so more bouncing. This type of detector, though, is really great for positive ion detection according to Kitson, but it can be reversed as well in order to detect negative ions. Next, we have time of flight with the Dally detector pair. Now, this, as the name implies, will measure the ion's time of flight in the flight path tube. By using electric fields, it goes and accelerates the ions. So it'll add energy to the ions to move them through. Now, the trick is, though, all ions, by passing through this, will have the same kinetic energy. So that way, their entire time of flight is based solely off of mass or the weight of the actual ion. Heavier ions are going to move faster according to emissions analytic. This is just due to the fact that they're bigger, and so they're going to move a lot quicker through that tube. Now, as they move through that tube, they are going to go through towards the Dally detector, which is pictured at the bottom. They bounce off of the Dally knob, and the Dally knob directs it towards the photomultiplier or the reflectron. So the reflectron is what's going to amplify the resolution. And then this reflectron will bounce it off once again. Now, what's interesting about the Dali detector is that the photomultiplier is actually kept separate from the vacuum. This is what's going to preserve the lifespan of the instrument. It's also going to lead to less contamination and better acceleration according to Chronologic. With that, also, the Dali detector is great for detecting multiple ions at the same time, unlike the specificity of the quadrupole detector. Now that we know about these mass analyzers and the detectors, what types of chromatography go well with these mass analyzers and detectors? Starting with the quadrupole and the continuous diode electron multiplier, this one pairs well, according to Taylor, with all types of chromatography, so LC, HPLC, and GC. Now, depending on the sample, though, this will determine what type of chromatography can be used. So if the sample can't be volatilized, then it won't be used with GC. It's very good, though, for chemical and biological samples and liquid physical as well. This is just because you don't want any degradation of the sample when going through the chromatography techniques. And it's very, very good, again, for that specific type of analysis. Now, the time of flight with the Dali detector pairs extremely well with GC, and it will be seen with it quite often. Now, once again, the same thing applies. Some samples can't be volatilized. If they can't be volatilized, you might not be able to use time of flight and specifically the Dali detector with it. You might need to go to the quadrupole analysis. But it's very good for some biological samples, providing that you don't actually degrade the sample in the process of volatilizing it. Physical samples and some chemical samples. Ones that it won't work on are ones where there's going to be a toxic or very poor reaction, such as pesticides. But basically, the pairing of these types of methods with the detectors and mass analyzers is going to allow for less confusion and a clearer identification of mixture components, as confirmed by Jones in his article. Now, how all of this relates to each other, or to summarize everything that we just talked about right now, the type of sample that you encounter is going to dictate the type of sample preparation technique. It's going to determine whether or not you need to use an extra extraction technique or what type of component that it needs to be dissolved in order to prep it prior to running it through chromatography. One of the questions that can help with that is asking, can the sample be volatilized? Because if it can't, then you're going to be going with the LC or the HPLC techniques. Now, ions are going to be separated with chromatography at the start, but then further analysis is going to be performed by the mass analyzer and the detector. And again, the type of chromatography will help to determine what type of mass analyzer and detector is good to pair with it. This way, at the end of it, you not only have chromatography, the results are the chromatogram, you're also going to have a spectrogram to go along with it and provide you with much more information as well as a clearer result. That's all that I have for you today. These are the references if you would like to know more. Thank you, Alda, for attending this training. Have a good day. Professor, my link will be included to this video at the end of my slideshow presentation. Thank you.